Holidays in my family are festive, cozy, and filled with love. Right up until somebody gets the same Secret Santa assignment they had last year. So, to avoid a repeat of the great Secret Santa incident of 2019, we decided that humans cannot be trusted with drawing names. So naturally, I wrote a PowerShell script to do it. In my family, there are 5 siblings, their spouses, all my nieces and nephews, and my mom. Throw in my wife and kids, and that's over 20 people, which means when it comes to Secret Santa, I'm not drawing names from a hat. I'm navigating a genetic minefield. Sure, we say we're doing Secret Santa, but what we're actually doing is solving a constrained matching problem. A miniature computer science puzzle disguised as holiday cheer. And sure, I may tell my family we're doing Secret Santa, but what I'm actually doing is solving a constrained matching problem. A miniature computer science puzzle disguised as holiday cheer. Think about it. Every person must be assigned exactly one receiver. Obviously nobody can get themselves, but we also don't want immediate family members assigned to each other. And absolutely nobody should get the same person they got last year, lest we forget 2019. What we're really building is a matching algorithm, a system that takes 2 identical sets of people and finds a perfect one-to-one mapping between them, while obeying a list of rules stricter than some IT security policies. From an automation perspective, this is the same kind of logic you would use for assigning workflows to servers, pairing mentors and mentees, creating tournament brackets, scheduling resource allocations, or matching inputs to outputs in any structured workflow. Today, we're using Secret Santa as our playground, because nothing motivates learning like the fear of accidentally assigning somebody the wrong person and causing a domestic gift-giving incident. Nobody wants to be that uncle. So by the end of this video, you'll have a smart, fair, and totally hands-off Secret Santa generator. But you'll also have a reusable algorithm pattern for matching 2 sets of data under any constraints, all using nothing but PowerShell, a CSV file, and sheer festive determination, or fear of retribution from your 3 sisters. But maybe that's just me. So grab your hot cocoa, pretend it's computer science school, but with more elves, and let's build a constrained solving engine that just happens to hand out gifts, all while avoiding family feuds. So let's jump in. First, we'll start by defining our criteria. We want to take a list of names, preferably from a CSV, and assign 1 person to each. However, there are a few caveats. First, we want to make sure that nobody draws themselves. Then, we'll prevent people from drawing members of their immediate family, so husbands and wives don't end up getting assigned to each other. And finally, we'll record a history, so you don't get the same person 2 years in a row. We'll start with a simple CSV, just names, no holiday drama. Yet. First, we need to create our data. I'm just going to populate some random people into this and save it as a CSV. This CSV is what our script will use to populate the list of givers and receivers. Now, we'll start at the very beginning, importing our list of participants. Import CSV pulls in participants and turns each row into a PowerShell object with properties like name and family. If I dump participants to the screen here, so we can have a simple sanity check of the data before we do anything clever with it. If this part is wrong, everything downstream is just festive nonsense. So the first, most obvious idea for Secret Santa is take a list of people, shuffle it, line it up against the original list. That's what this line does. We take participants, pipe them into getRandom with the count equal to the number of participants, and that gives us a random permutation of the same people. I'm calling that receivers. And if we print it out, we see the same folks as before, just in a different order. Like when you shuffle a playlist, only this time it's your family members. Now, for the world's simplest Secret Santa algorithm, we just connect each person to the shuffled list by index. This for loop walks from 0 up to the number of participants. For each I, we grab participant I as the giver and receiver I as the receiver and print out the results. Super simple, super fast, and super broke. Because with this approach, people absolutely can get themselves. We're not checking anything. We're just hoping the universe is kind. And spoiler alert, it isn't, as we can see by Alice down here. So let's try this again. New script tab, same basic idea. We start with our random permutation of people, receivers as a shuffled version of participants. But this time, instead of just printing the pairs and calling it a day, we're actually going to check whether the assignment is valid. Here, we start to grow our logic. We create an empty array, pairs, where we'll store only valid giver and receiver combinations. We walk through each index again. Giver is the original participant in this position, I, and receiver is the shuffled one from the same position. Then we add one simple rule. Giver name equals receiver name, break. If the giver's name and the receiver's name are the same, that means we have signed somebody to themselves. That's not allowed. So we bail out of the loop with a break. If they are not the same, then we add a nice little object to pairs, which just gives the giver and receiver's name. At the end, we print pairs to see what we got. The catch, if any self-assignment happens, we break early and end up with an incomplete list. So we've gone from always wrong but complete to sometimes okay but often half-baked. But I think we can do better. So how do we fix that? Easy. We just keep trying until it works. Here we introduce max attempts equals 1,000. This is our safety limit, so we're not going to shuffle forever. Then we wrap our pairing logic in a for loop that runs up to 1,000 times. Each pass through this loop represents one attempt to find a valid shuffle. Right after we build our list of pairs for a given shuffle, we introduce the new variable valid equals true. The idea is we'll assume this attempt is valid unless we catch it breaking a rule. If we hit self-assignment, we flip valid to false, so we know that this shuffle is bad and we need to try again. Now, inside the give name if check, we do more than just break. We set valid equal to false. That gives us a way to remember that this entire attempt failed due to self-assignment. So we break out of the inner pairing loop, and then we check valid. We'll know that this run isn't acceptable and we should shuffle again. Once we've either finished building pairs or bowed out entirely, we should check valid. If valid is still true, that means we made it through everyone without hitting a self-assignment. In that case, we copy pairs into assignments, print a happy little message giving our number of valid attempts, and we break out of our outer loop, and we're done. If valid was set to false, we don't do any of that, and the outer loop just runs again with a fresh random shuffle. At the end, we print assignments. That's either a valid list of non-self pairings or null empty if we somehow failed at all 1,000 attempts, in which case your Secret Santa group is statistically cursed. Now, if we're honest with ourselves, we've basically just built a brute force derangement generator. We keep shuffling the list until nobody gets themselves or until we give up. It's simple, it works for small groups, and it's a great starting point, but it doesn't know about families, it doesn't remember last year, and it's still mostly us begging randomness to be kind. But if you've ever watched any of my past videos, or you look at the runtime below, you'll know that we're just not going to leave it here. Now, our first attempt used the shuffle and pray approach, which we can call festively suboptimal. This brute force attempt just randomly shuffles, checks constraints, and if it fails, it throws everything away and repeats. AKA the Secret Santa equivalent to rebooting Windows to see if it fixes itself. But let's do something smarter. This isn't a problem of who's going to get assigned Aunt Judy. It's really find a permutation where each giver gets exactly one receiver and all these constraints hold. No self, no same family, and no same person as last year. Mathematically, this is a perfect matching on a bipartite graph. Left side givers, right side receivers, lines between giver A and receiver B if the pairing is allowed. Then you find a perfect matching where every giver is matched to exactly one receiver. Now, if we're feeling extremely academic and perhaps a little too pleased with ourselves, we could break out the Hopcroft-Karp algorithm, which effectively finds the maximum matching in a bipartite graph by repeatedly using breadth-first search and depth-first search to identify and augment along the shortest alternating paths with a runtime order E root V. Whew. But let's be honest, this is Secret Santa, not a PhD defense. So we'll take the practical route, skip the dissertation, and use backtracking with a few smart choices, which gets us almost all the benefits without a chalkboard covered in Greek letters. We'll start by giving ourselves a friendlier variable. Participants is what comes from the CSV. But for the rest of this logic, I'm going to call them givers, because each one of these people is going to give a gift, whether they like it or not. Next, we're going to build a map of options for each person. Basically, who is this person allowed to draw? We start with candidate map as an empty hash table. That's going to be our lookup, where the key is the giver's name and the value is a list of people they're allowed to get. Then we loop over each giver in givers. Inside the loop, we create valid receivers by filtering the list of all givers. For now, we're only going to have one rule, no self. So we keep everyone whose name is not equal to the giver's name. So you're not buying yourself a present, because that's just shopping. Once we get that list, we shuffle it using the get random. This gives us the same people, but in random orders, so that we don't always get the same exact Secret Santa results every time we run the script. And finally, we stash that randomized list into the candidate map under the giver's name. So now candidate map Alice is everyone Alice is allowed to give to in random order. Now we can look at the candidate map and see what the algorithm thinks is valid at this stage. As a quick sanity check, I like to peek at how many options each person actually has. I'm selecting the calculated property called count that looks up the number of valid recipients for each giver in the candidate map. That shows me that for every person, how many valid receivers they currently have, and then shows the rest of their properties. If somebody has 0 options here, I know I've broken something. The 6 next to everyone is expected, since we are only filtering on self. Everybody should be able to be assigned to everyone else, hence 6. Now, let's make this more realistic. In most families, you don't want somebody drawing their spouse or kids. That's not Secret Santa, that's just Santa. So right after the no self rule, I'm adding another condition, no same family. If the receiver's family matches the giver's family, they're out. So now valid receivers is filtered by 2 rules, no self, no same family. The candidate map will shrink a bit here, especially for larger families, but that's exactly what we want. Some of the people have lots of possible receivers. Others have just a few. To make the search more efficient, we'll sort givers into ordered givers, based on how many candidates they have in the candidate map. The people with the fewest options bubble to the top. That way, when we start assigning, we can deal with the tricky people first, and if the whole setup is impossible, we find out sooner rather than later. When we look at order givers, you can see the order we'll process them in. These are our givers, sorted from piggiest constraints to the eternal bachelor uncle. Right now, our candidates are in a hash table keyed by name, and our givers are in a sorted array. To make the algorithm easier to write, we're going to convert everything into a nice index-based structure. We can create an empty array called candidates by index. Then for each giver in ordered givers, we look up their list of candidates in the candidate map and push that entire list into the candidates by index. The important thing here is that order givers 0 lines up with candidates by index 0. Order givers 1 lines up with candidates by index 1, and so on. This makes the next step, the actual matching, way less brain melting. Now, we're going to set up a few variables that drive our holiday matchmaking. Giver count is just how many people we're assigning. Next candidate index is an array of integers, 1 per giver, initialized to 0. It tracks which candidate we'll try next for each giver as we go. Used receivers is a hash table we'll use to mark which receivers have already been assigned so that nobody gets more than one secret Santa. Receivers by depth is an array, 1 slot per giver, where we'll store who ends up getting assigned at each step. Think of it as the current draft of our final parent. And depth starts at 0, which is our index into order givers. You can think of depth as which giver are we working on right now. And here's the heart of our algorithm, a while loop that keeps going until depth equals giver count. When depth equals giver count, that means we've assigned everybody and we're done. Until then, we keep working. Inside the loop, we grab giver, the person at this depth in the order givers, candidates, that's the person's list of possible receivers, and I, which candidate index we're trying for this time. Then we grab receivers at candidate I, and then immediately bump next candidate index for this depth to +1. So next time at this depth, we move on to the next candidate. When we check if the receiver has already been used, that's where used receivers comes in. If this person has not already been taken, we mark them as used, store them in the receiver by depth at this depth, and then increment the depth to move to the next giver. If they are already used, we use the continue to loop back to the beginning and try the next candidate for this same receiver. So the loop moves forward, assigning receivers, but can step backwards when it gets stuck, trying different combinations until it gets success. But what happens if there are no more candidates available? Well, if that happens right now, you'll see a bunch of red error messages and you'll be stuck in an infinite loop. So before we try the next candidate, we check to see if we've already tried all of them. If I is greater than or equal to the candidates count, we're out of options for this giver at this depth. That means whatever choices we've made from the previous givers paint us into a corner, and now it's time to backtrack. We reset next candidate index for this receiver back to 0, so that when we come back, we start fresh. If the depth is 0 and we're stuck, that means there's no valid assignments under any of these rules. So we throw a helpful yet slightly dramatic error. Otherwise, we step back one level by decrementing depth. We look up the previously assigned receiver on receiver by depth, remove them from the used receivers, and then clear that slot. Then we continue, which jumps back to the top of the loop and tries a different receiver for the previous giver. This is basically the algorithm saying, that path didn't work. Let's undo that move and try another branch. Now, once we've escaped the while loop, it means the depth has reached their giver count, and we've successfully assigned every giver a unique receiver. Now we turn that internal state into something friendly. We loop from 0 to giver count, and for each index, we create a PS custom object with giver set to the giver at that index in the order givers, and receiver set to the receiver we stored at that same index in receivers by depth. That gives us a clean list of givers and receiver pairs in assignment by name, which we'll output so that you can see the final map. And then finally, to make this human readable, we pipe the assignment into for each object and format each pair as a simple arrow. Giver name to receiver name. This makes it easy to eyeball the results and confirm that nobody got themselves, nobody got somebody in the same family, and every receiver only shows up once. So at this point, we've effectively built a small matching engine that obeys all of our rules and still manages to look like holiday magic. Before we continue on, let's take a quick look at a visualization. So what you can see here is a representation of our order givers and our candidates by index at each depth. And we'll step through how our algorithm is working. All right, so we start at depth 0 and we select Alice as our giver, and we assign the first candidate by index, in this case Dave. Check, is this receiver used? No? Great, then we'll mark Dave as used. Go down to our next one, Bob at depth 1. Assign Alice. Is Alice used? No? Great, mark her used. Let's move on to our next depth. Now we're at Carol at depth 2. Assign Alice. Is Alice used? Well, yes, she is. So we go down to the next candidate, Dave. Is Dave used? Well, yes, in this case, Dave is used as well. If Dave wasn't used, we would assign here and we would move on. But since it's already been used and we don't have any other choices here for Carol, we need to backtrack. So what we're going to do is we're going to revert back to Bob, remove Alice from our used receivers, and then continue from where Bob left off. So Bob, now at 1, is going to assign Carol. Carol is not used, so we're going to mark Carol as used now for Bob. Now we can come back to Carol at depth 2 again, and we check Alice. Alice is no longer being used, so that we mark Alice as used for Carol, and then we continue on down through our process. And this will continue stepping back up and down until it is able to find a path that works and everybody is able to receive one candidate. But wait, there's more. Now it's time for our Secret Santa script to stop being a cute little shuffle and start developing long-term memory and reusability. Before, Givers was just a straight copy of participants. Now we're getting a bit fancier. I'm piping participants into select object to reshape that data into something that's better for our matching logic. I'm building 3 properties. Name, a combined display name for the first name plus the family, which we'll use as a unique identifier in our pairing logic because our previous attempts didn't account for multiple people with the same first name, which, coming from somebody with a family with 4 Daniels, you would think I would know better. You could use an integer or a GUID to truly ensure that they are unique, but to make things easier to visualize here, we'll stick with first name and last name. Then we'll just put their original first name in as first, in case we want to use it later. Then family is the same as before, so we can continue to avoid pairing immediate family members and triggering awkward conversations at Christmas. And let's take a quick look at Givers so we can see exactly what we're working with. Cleaned up, normalized name data, ready for algorithmic abuse. Next, we're going to give our script something truly terrifying. Memory. Here, I'm importing Secret Santa 2024. This is the file that we exported last year with all the giver and receiver pairings. I store that in last year's assignments and then dump it out so that we can confirm the structure. Each row should have at least giver and receiver column. This is the data that we'll use to enforce the rule, don't give the same person 2 years in a row. Now, we'll transform that CSV into something that is fast and easy to query. We'll create an empty hash table called last year's pairs. For each row in last year's assignments, we'll do a quick sanity check to make sure that both giver and receiver are populated. If they are, we'll build a key like giver name, pipe, receiver name. For example, Alice Smith, pipe, Bob Jones, and store that in the last year pairs with the value of true. This gives us an instant lookup. Did Alice Smith get Bob Jones last year? Just check, not last year's pairs. Alice Smith, pipe, Bob Jones. I output last year's pairs so you can see the keys that we've built. It's not pretty, but it's efficient, and efficiency is beautiful on the inside. Now, we're back to building the candidate list for each giver, but this time, we're layering in more rules. Candidate map is still our trusty hash table where each giver name maps to the list of people they can validly draw. The first 2 rules are the same as before. No self, no same family. So far, this matches the behavior from before, but here's the new twist. No same pairs as last year, so we'll add a lookup on the giver name, pipe, receiver name in the last year's pair. If that key exists, it means that the giver and receiver pair already happened last year, so we reject. If the key is missing, the pair is allowed and we can keep it. Now, our valid receivers only include people who are not the giver, not in the same family, and not last year's recipients. This is how we keep the gift exchange feeling fresh, instead of forcing Bob to awkwardly buy socks for the same person every year until the sun burns out. However, we now need to check if we've accidentally over-constrained somebody. If our valid receiver count is 0, that means this poor soul has no legal options under any of the rules that we defined. At that point, the entire problem is impossible. So we throw a clear error, rather than quietly generating a broken Secret Santa. If we do have valid options, then we randomize them with the get random so the order is different on each run. Just like before, we drop that randomized list into the candidate map keyed by the giver's full name. From here on, the matching logic, ordering givers by difficulty, doing a depth first search with backtracking, is exactly the same as before. We're just feeding it a smarter candidate list that now respects history as well as family. Once the search logic has found a valid set of assignments, we build a simple history-friendly view of the result. We loop over each index, and for each position, create a custom object with just 2 properties. The giver, the full name of the giver at that index, and receiver, the full name of the receiver we matched them with. And this is the shape we want from our history file. A neat list of who had who this year. I output assignments by name so we can confirm everything looks good before we serialize this into future success. At this point, our logic is doing all the real work and is probably worth keeping. So we're going to wrap everything into a function called get Secret Santa assignment. As always, we'll mark it with commandlet binding so it behaves like a proper advanced function. meaning we get all the goodies like dash verbose built in. The function then takes in participants, which is the raw people loaded from our CSV, and last year's assignments, which is optional. And if we do pass it, we'll enforce the no repeat rule. If it's empty, we behave like it's year one. We also add a basic sanity check. Fewer than 2 participants, we throw a no single player secret Santa. All the logic we just walked through, building givers, last year pairs, candidate maps, running the mapping loop, and returning assignment by name, now lives inside this function. That makes it easy to reuse and test and call for different scripts later. Now, outside of the function is the orchestration layer. This is where we plug in our functions to the actual files. Set participant paths to the participants list in the previous path to last year's Secret Santa assignment. We import the current participants into participants, and for previous, we're a bit more careful. If we only want to import if the file exists. So if it exists, we get last year's assignment. If not, we just set it to null, and our function will act just like it's year one. This lets you run the same script every year without having to babysit your inputs. Now, the fun part. We actually call our function. We pass in the current participants and whatever we manage to load into previous. The function does all the heavy lifting. Avoid self pairs, avoid family pairs, avoid last year pairs, searches until it finds a valid mapping, or proves it doesn't exist. We store the results in assignments, and then we pipe it to the format table so that we get a nice readable table in our console. And this also works as our sanity check step to make sure everything looks right before we commit to disk or to our family. And finally, we serialize our genius to disk. We take assignments and export them to a CSV named with the current year. For example, Secret Santa 2025. And we'll even use UTF-8, so everybody's name survives the round trip, even if they have those fancy accents. And then this file becomes next year's last year assignment, which means every December, the algorithm gets a little bit smarter and the chances of accidentally repeating pairings goes down. So there you have it. We built a fully automated, family-aware, history-aware Secret Santa engine, which, let's be honest, it's a hilariously over-engineered solution to not want to draw names out of a hat. We started with a naive shuffle, upgraded to backtracking, with better judgment sprinkled in, and some real computer science concepts, and walked away with a system that can handle family, histories, and holiday chaos with a level of sanity humans simply cannot be trusted with in December. What's great is that this same logic applies far beyond Secret Santa, matching people to tasks, assigning on-call rotations without repeats, balancing workloads, distributing resources. Anytime you have 2 sets of things that need to be matched under rules, this approach absolutely shines. If you found this useful, please hit the like, subscribe, and maybe share with that one relative who insists on running the gift exchange with an Excel sheet from 1998. And as always, all the code from this and all my other videos can be found at douse.dev. And until next time, happy holidays, and may your Secret Santa assignments never require therapy.